Hello and welcome back. I'm excited to welcome you to our series our series of videos on sequences and series. This is a really cool chapter in calculus, and it's kind of unlike what we've been studying previously with derivatives and integrals, though you'll see some things that we have studied before, such as limits, come into play. But I really find this section interesting. I hope you do as well. Let's jump right into it, figure out what these things are. So our first video will be on sequences, then we'll dive into series, and then we'll get into some special things. So let's get into it. Well, what's a sequence? It's kind of exactly what it sounds like. Mathematically, we can describe it as like a collection of objects, in this case numbers, in which repetitions are allowed, but the order of our numbers do matter. So a sequence can be thought of as a mapping of values to positions in the sequence. So we see in this little diagram down below, the thing on top is what we would consider a sequence. 1, 2, 3, 4, 5, etc., etc. You know, we've known a sequence since we were 1 or 2 years old. Pretty crazy, right? But what we're going to do is establish this mapping, where 1 will be mapped to something which we'll call a sub 1. So, and 2 can be mapped to something which we call a sub 2. So you can think of our sequence being called A, and then we can denote a specific term by giving a subscript. So a sub 4 would be mapped with 4. So a sub n is defined to be the nth term of the sequence. If we're given a formula for a sub n, then we can just compute our sequence, right? Because we have our formula, we just need to give our values for n, and we know our sequence. So now that we kind of understand what a sequence is, let's take a look at a couple of example sequences. So here we go. We're going to start by listing terms of a sequence. So suppose we're given this formula, a sub n equals 3 plus negative 1 to the n. We want to figure out what is this sequence actually. We have a nice little formula, but it's sometimes helpful to list out the terms. So what would the first term of this sequence be? Well, for the first term, we would want n to equal 1. Remember before, we let the first term of our sequence here be denoted a sub 1. So same thing here, we want to compute a sub 1. So where we see the letter n, we'll put a 1, and we get 3 plus negative 1 to the power of 1, which is equal to 2. That's the first term of our sequence. What about the second term? That's a sub 2. So now we put n equals 2 into our formula, and we get 3 plus negative 1 to the power of 2, which is equal to 4. For the third term, it would be 3 plus negative 1 to the power of 3, which is equal to 2. And for the fourth term, 3 plus negative 1 to the 4, which is equal to 4. So the sequence is 2, 4, 2, 4, and you can sense a pattern here, and whatever pattern you're hypothesizing is most likely the actual pattern here. The sequence just alternates between 2s and 4s. Let's look at another sequence. So suppose a sub n equals 1 over 2 to the power of n. So again, we want to find the first term, we put n equals 1, so that would be 1 over 2 to the power of 1, which is a half. A sub 2 will be 1 over 2 squared, which is 1/4. Then we get 1/8 for our third term, 1/16 for our fourth term. And we can see that our sequence is a half, a quarter, an eighth, a 16th, etc., etc. So these are a couple of examples of sequences. However, not all sequences are just going to be given in terms of n. Sometimes our sequences or our terms will rely on previous terms, and for that we look at recursive sequences. So a recursive sequence is a sequence where new terms depend on the values of previous terms. What does that mean? Well, let's take a look at an example definition of a sequence and figure out the terms. So suppose a sub n plus 1 equals a sub n minus 5. And a sub 1 equals 25. So our sequence definition is given here, but we're also given the first term of the sequence. So now we want to define perhaps the second term of the sequence, a sub 2. So for that, we can turn to this equation here. And to find a sub 2, well, we see two different a things in that equation. There's a sub n plus 1 and a sub n. So suppose we let n equal 2, because that's what we're after, a sub 2. If we let n equal 2, then we'll have a sub 2 plus 1 equals a sub 2 minus 5, or a sub 3 equals a sub 2 minus 5. But that doesn't tell us what a sub 2 is, because we don't know what a sub 3 is. So to find a sub 2, we want this term here to be a sub 2, which means n would have to be 1. And you can see that when we write this out, we'll get a sub 1 plus 1 equals a sub 1 minus 5, or a sub 2 equals a sub 1 minus 5. Now, a sub 1 isn't a number yet, until we realize that we are given a sub 1. So a sub 1 minus 5 is equal to 25 minus 5, because we're given a sub 1 equals 25. So a sub 2 will equal 20. However, notice that the value of a sub 2 relies on a previous term, which is a sub 1 in this case. Will that dependency always be there on only a sub 1? Well, let's figure that out. So the first box will tell us that a sub 2 is indeed equal to 20. What about if we were to find a sub 3? Now, we would substitute n equals 2 in, because that would make this a sub 3. And then we get a sub 3 is equal to a sub 2 minus 5. So now our equation is saying, hey, don't depend on a sub 1 anymore, now depend on a sub 2. So we see now we'll substitute a 20 for a sub 2 instead of this 25. And then we still subtract this 5 from before, and we get 15. Cool. And then we do a sub 4. So we can start to think a sub 4 will be a sub 3 minus 5, which would be 15 minus 5, which is 10. Right. A sub 5, do the same exercise, you should get equal to 5. And that means our sequence is 25, 20, 15, 10, 5, etc. Let's take a look at another one. So now we have a seemingly more frightening equation, where a sub n plus 2 equals a sub n plus 1 plus a sub n. We're given a sub 1 equals 1 and a sub 2 equals 1. So we want to find a sub 3. A handy trick that most of the time works is that the thing on your left will be what you want to try to solve for. So a sub 3, we want to make this a sub 3, so we should let n equal 1, because 1 plus 2 equals 3. So that's saying a sub 3 will equal a sub 2 plus a sub 1. A sub 2 is 1, a sub 1 is 1, 1 plus 1 is 2. So a sub 3 is equal to 2. So I'm going to start writing out the terms of the sequence. So we have 1, 1, 2. And now what I'll do is I'll draw these arrows. So what is the meaning of these arrows? Well, if we have an arrow pointing from, say, A to B, generally, that means the computation of A depended on B. So in this case, we have an arrow from 2 to 1, which means the computation of getting that value 2 depended on the value 1. And let's see how these arrows change as we move along. So now we need a sub 4. So we'll have this be a sub 4, which means n should equal 2. So a sub 4 will equal a sub 3 plus a sub 2. A sub 3 is 2, a sub 2 is 1. So a sub 4 should equal 3. So we can add 3 to our sequence here. And we know that that depended on the 2 from before and a sub 2, which is equal to 1. And we can do this. We can compute the next term, which will be a sub 4 plus a sub 3, which is 3 plus 2, which is equal to 5. So we can add 5 here, add in some arrows. And then finally we can compute a sub 6, which will be equal to 5 plus 3, which is equal to 8. And then maybe add some more arrows here. And the point of this illustration is to show that these dependencies are changing. And that's the beauty of these recursive formulas, that we can succinctly represent these dependencies with one simple equation. But notice the amount of things that we depend on are staying the same, because on the right-hand side of this equation, there are 2 terms that we're just summing together. It's just the terms that are different. So this sequence ends up being 1, 1, 2, 3, 5, 8, and you may recognize this sequence as the Fibonacci sequence, one of the most famous sequences, and it can indeed be represented recursively. In fact, that's how it's most commonly represented. Okay, so you're probably like, this is cool and all, but where's the calculus? This is just me doing algebra, right? Well, what's really interesting about studying these sequences is seeing what happens as we continue listing out terms. Here we've just listed out the first few, but what does the 100th term look like? What does the 1,000,000th term look like? As we keep on plugging in these values for n, as n gets larger and larger, what does our sequence look like? So that's what we'll look at. Sequence convergence. Do these terms at the end of the day, when n is really, really large, as n approaches infinity, do these terms approach some value? That's sort of what convergence is. Let's take a look at it. So if a sequence has terms which are approaching a certain limit value, then we say that the sequence converges. So, for example, we saw the sequence 1 over 2 to the n, and we said that its terms are 1/2, a fourth, an eighth, and so on. And you can tell that these terms are getting smaller and smaller. 1/4 is smaller than a half, but 1/8 is smaller than a fourth. 1/16 is smaller than an eighth, and so on and so forth. But we never get to a negative number. So we should be thinking that this sequence will eventually reach something really, really close to 0. And indeed, the sequence does converge to 0. So to determine convergence, and to determine what value a sequence converges to, we can simply take the limit as n approaches infinity of that sequence, the formulaic version of that sequence. If we compute this limit and obtain a single finite number, then we can safely conclude that the sequence converges. But if we do not obtain one particular value, or the limit does not exist, reaches infinity or negative infinity, then we'll say that the sequence diverges. So that's where the calculus will start to come in. There's going to be a lot of stuff about limits here. So let's take a look at a couple of examples and then try some for our own. So we have this sequence here that we saw before, 3 plus -1 to the n, and we said that the terms were 2, 4, 2, 4, etc., etc. But does the sequence converge to anything? What's the limit as n approaches infinity of this sequence? Well, we can take the limit as n approaches infinity of a sub n. A sub n is this equation we're given here. So we're computing this limit here. Let's bring the 3 out front, because the limit as n approaches infinity of a constant is just that constant. And then we're left with the limit as n approaches infinity of -1. But what's that equal to? -1 to the n oscillates between -1 and 1. It goes back and forth, back and forth. It doesn't really have a limit. And so in this case, we would have to include that the limit does not evaluate to one value, so the sequence diverges. So let's take a look at a different example. We're going to get a series here, a sub n equals 1 over n, and we want to see if it converges and to what value. So what would the first few terms of this sequence look like? Well, a sub 1 would be 1 over 1, which is 1. A sub 2 would be 1 over 2. A sub 3 would be a third, a fourth, a fifth, and so on. And we can start to hypothesize what the answer would be, that each term is successively smaller than the previous term, in fact, the previous terms plural, and we're getting smaller and smaller. It seems like we're approaching 0 because we never dip into the negatives. The equation has no negative in it, so it should be 0. We can check this mathematically by taking that limit, the limit as n approaches infinity of 1 over n, and indeed we know that that is equal to 0. So we would conclude that the sequence converges to 0. Pretty cool, right? Let's try to do a couple of examples on our own and see what we can conclude. So here we have an example. Determine if the sequence converges, and if so, to what value. So before we get into the actual math, I like just listing out a couple of terms just to see what it looks like, maybe get some insight into what the answer could be. So a sub 1 is going to be equal to 1 plus 1 factorial over 1 factorial, which is 2 factorial over 1 factorial, which is 2 over 1, which is equal to 2. A sub 2 is going to be equal to 2 plus 1 factorial over 2 factorial. You can compute this out. This is 6 over 2, which is equal to 3. A sub 3, I'll just write it out now. This is 24 over 6, which is equal to 4. a sub 4 is equal to 120 over 24, which is equal to 5, and so on. And we're starting to sense a pattern that our sequence is looking like 2, 3, 4, 5, so on. So maybe it's just going up by 1. So we should be thinking that maybe this sequence won't converge, because we're just going upwards and upwards, probably to infinity. But in order to prove our hypothesis, we should compute it mathematically. And to do that, we have to compute the limit as n approaches infinity of a sub n, which is equal to the limit as n approaches infinity of n plus 1 factorial over n factorial. Well, n plus 1 factorial can be decomposed a little bit, right? This can be rewritten as n plus 1 times n minus 1 times n minus 2 times times like 2 times 1. And in the denominator, we can think of n factorial as n times n minus 1 times n minus 2 times times 2 times 1. And we should see here that a lot of things will cancel, right? The 1's cancel, the 2's cancel, the dots cancel, the n minus 2's cancel, and so on. And in fact, we're left with the limit as n approaches infinity of n plus 1. What is this limit equal to? Well, you can just like directly substitute n infinity, and you should get that this is equal to infinity. Therefore, the sequence diverges. That is our conclusion. And that matches what our hypothesis was, so we should be feeling pretty good about ourselves. Good job. Let's do another question. Determine if the sequence converges, and if so, to what value. Okay, this one's a little bit more hefty. Let's try listing out a couple of terms. So a sub 1 is equal to 1 squared over 2 to the 1 minus 1, which is equal to 1, I believe. A sub 2 will be 2 squared over 2 squared minus 1, which is 4/3. A sub 3 is 3 squared over 2 cubed minus 1, which is equal to 9 over 7. A sub 4 is 4 squared over 2 to the 4th minus 1, 16 over 15. Do a couple more. 5 squared over 2 to the 5 minus 1, which is equal to 25 over 31. 6 squared over 2 to the 6 minus 1, which is 36 over 63. Okay, so can we conclude anything here? Let's look at the general trajectory of the numbers. So we go from 1 to 4/3, which is an increase. 4/3 to 9/7 is a slight decrease. 9/7 to 16/15 is a slight decrease, but 16/15 is still greater than 1. From 16 over 15, we go to 25 over 36, which is a decrease. 25 over 31 to 36 over 63 is also a decrease. So we're getting smaller and smaller, which is perhaps a good sign for sequence convergence, but let's take a look at this and actually compute it mathematically. I'll move this off to the side. We want to find the limit as n approaches infinity of a sub n, which is equal to the limit as n approaches infinity of n squared over 2 to the n minus 1. If we were to just plug in the infinity for n, we'll get infinity squared on the numerator, which is just infinity, and in the denominator 2 to the infinity is just infinity, minus 1 is still the infinity. So that is an indeterminate form, which means we have to call on our good old friend L'Hopital and use his rule to evaluate this limit. So we can say, using L'Hopital's rule, the limit as n approaches infinity of n squared over 2 to the n minus 1, what we're trying to solve for, is equal to the limit as n approaches infinity of the derivative of the numerator divided by the derivative of the denominator. So the derivative of the numerator, that should be pretty easy, that's just 2n. The denominator might be a little bit tricky, where it's 2 to the n. We don't really take the derivative of that very often. How actually are we going to compute that derivative? Well, let's take a look down here. So we're just going to handle this separately. So we want to find the derivative with respect to n of 2 to the n minus 1. which we know is equal to the derivative of 2 to the n minus the derivative of 1, which is just going to be equal to the derivative of 2 to the n. So let's let y equal 2 to the n. Then we're tasked to find what dy dn is. Okay, well, we can calculate this by doing a little bit of implicit differentiation. But for that, we need to use a little trick. Let's take the natural log of both sides. So if we were to take the natural log of the left side, we get ln of y, and on the right, we get ln of 2 to the n. And hopefully you remember your rules about limits, because this right-hand side comes to n ln of 2, which is really nice to work with, because now we don't have that 2 to the n. And on the left, we still have ln of y. Now we'll do our implicit differentiation. On the left-hand side, we'll get 1 over y times dy dn. And on the right-hand side, we can use the product rule. So n times the derivative of ln of 2. ln of 2 is just a constant, so that's going to be equal to 0. But we add to that ln of 2 times the derivative of n, which is just 1. So now we can multiply through by y on both sides and get dy dn is equal to y times ln of 2. But remember, y is equal to 2 to the n. We want our derivative in terms of n, so we can say that this is equal to 2 to the n times ln of 2. So dy dn is equal to 2 to the n times the natural log of 2. So a nice little tangent there to review our derivatives, but now we can get back to the question. So our denominator will look like that, 2 to the n times ln of 2. If we plug in our infinity now, in the numerator, we get 2 times infinity, which is infinity. In the denominator, we get 2 to the infinity, which is also infinity. Which means, you guessed it, we have to use L'Hopital's rule again. So let's write that out. Using L'Hopital's rule, again, we are saying that the limit as n approaches infinity of 2n over 2 to the n times ln of 2 is going to be equal to the limit as n approaches infinity of the derivative of the numerator divided by the derivative of the denominator. So the derivative of the numerator is simply going to be 2, and in the denominator we can use the product rule again. So 2 to the n times the derivative of ln of 2, the derivative of the natural log of 2 is simply 0, and then we add to that ln of 2 times the derivative of 2 to the n, but we just computed 2 to the n, the derivative of 2 to the n. So that's going to be equal to ln of 2 times, I'll just write it out, the derivative of 2 to the n. But this term here is going to be equal to 2 to the n times ln of 2. So our limit simplifies into 2 over ln of 2 squared times 2 to the n. And now if we were to do direct substitution, we get 2 in the numerator, and then 2 to the n, 2 to the infinity in the denominator, which is infinity, that's going to be equal to 0. So we can conclude that it converges. And now it's a good thing to check, like, does this actually make sense here? And the answer is like, yeah, we started at 1, reached to like 4/3, and then just kept on going downwards, and all of these terms seem to still be positive. It didn't seem like we were getting below 0 at any time. And to just confirm that, is there anything here that would make us think that we would get a term below 0? Well, for that to happen, either our numerator would have to be negative or our denominator would have to be negative. N squared is never negative, and 2 to the n minus 1 is only negative when 2 to the n is less than 1. But when n is greater than 0, that will never occur, so our terms will always be positive. So having a value of 0 as our convergence value, that's a good sign, and indeed that's the correct answer. Let's do another example. So here we have the sequence a sub n equals n to the p over e to the n, where p is a positive integer. E is our famous Euler's constant, 2.718, 281828, etc., etc. But P is just a positive integer. Okay, so that means we can't really list out the terms because we don't really know what P is. But like, let's see, a sub 1 would be equal to 1 to the P over e to the 1, which is equal to 1 over e. A sub 2 is equal to 2 to the P over e squared, but that doesn't really tell us much, and so on and so forth. So that means we have to consider the limit. The limit as n approaches infinity of a sub n is equal to the limit as n approaches infinity of n to the P over e to the n. Well, we can try to plug in our infinity, and we get infinity to the P over e to the infinity. P is a positive integer, so infinity to the P would just be infinity, and e to the infinity would be infinity as well. So we have to use L'Hopital's rule. I'll just call it L'Hop. So that would say that the limit as n approaches infinity of n to the P over e to the n is equal to the limit as n approaches infinity of the derivative of the numerator divided by the derivative of the denominator. So the derivative of the numerator, we can compute that just by using the power rule, because P is a positive integer. So that would be P times n to the P minus 1. The derivative of e to the n is just e to the n. Do we gain any more insight from this? Well, if we plug in infinity again, we'll probably get infinity over infinity, which means we would have to use L'Hopital's rule again. So we can do that again, right? I'll just take the derivative manually now. So like in the denominator, we take the derivative of e to the n, that's still e to the n. The derivative of p times n to the p minus 1 is going to be p times p minus 1 times n to the p minus 2. And again, we get this dilemma of like, it's probably infinity over infinity, because n being infinity, that's just going to remain there. But when would we stop doing this? Like, if we have to continue doing L'Hopital's rule, when do we stop? Well, we'll stop when n doesn't have a power anymore, when the power of n is equal to 0. So we have to continue L'Hopitaling until this power is equal to 0. But since p is just arbitrary, we don't know when that will occur. So we can think, if we continue L'Hopitaling, we'll eventually get the limit as n approaches infinity. Our denominator will stay e to the n, but we'll have p times p minus 1 times p minus 2, etc., until we finally get times 2 times 1 times n to the 0. Right, that would be our last iteration of this power rule type thing. So now n to the 0, we can just ignore that entirely, right? And we're left with this limit here. But the numerator is just equivalent to p factorial. Our denominator is e to the n. Now what happens when we put in n? We get p factorial divided by e to the infinity. This is actually a lot more powerful. E to the infinity is just going to be infinity. But what is p factorial? P was a positive integer, which means p factorial will also be a positive integer, but it's a finite value, right? It's just a positive integer p, and it's smaller than infinity, so it's a finite value divided by infinity, which we know is going to be equal to 0. So the sequence converges to 0. So this is a very helpful thing to remember. If you see a sequence of this form, you can basically immediately know that it will converge to 0. So this is good. But it's time to be introduced to one of the fun theorems of calculus. I think it has a really cool name, and it's quite cool, actually. This is the squeeze theorem. But before we get into that, let's review some limit properties, as they'll help us in the long run. So suppose we have two sequences, a sub n and b sub n, and let's say their limits are L and K. Then the limit of the sum of the sequences is L plus or minus K. So what that's saying is that the limit as n approaches infinity of a sub n plus b sub n is equal to the limit as n goes to infinity of a sub n plus the limit as n approaches infinity of b sub n. So the limit sort of distributes. If we look into number 3 here, the limit of the product of the two sequences is equal to the product of L and K, so again the limit sort of distributes there. If we have the limit as n approaches infinity of c times a sub n, where c is a constant real number, that c factors out. And finally, if we're taking the quotient of two sequence values, a sub n over b sub n, again the limit sort of distributes to the numerator and denominator. We can compute those individually and still take the quotient. So let's take a look at the squeeze theorem. This says if we have two sequences, which we'll call a sub n and b sub n, and suppose they converge to the same value, which means the limit as n approaches infinity of those sequences is the same, which we'll call L. And now suppose there exists any integer capital N, just some integer capital N, such that for a third sequence, that sequence's terms always fall in between the other two sequences for all terms greater than that capital N, then the limit as n approaches infinity of that new sequence c sub n equals L, which is our limit from before, which sounds super complicated, but I assure you this picture will clear up a lot of things. So let me get a highlighter out. So we have a sub n and b sub n, and these two lines, these two red lines, represent these sequences. What we're doing is we're sort of plotting where the sequence is for each value. So a sub 1 has its point here, a sub 2 has its point here, a sub 3, etc., etc. Same with b. And we said, hey, those sequences have the same limit. As n goes to infinity, they're both approaching what appears to be 0 here. So those two sequences, we know that's sort of what we're given. But now we have this mysterious third sequence, c sub n. And we say, hey, when we reach this point here, capital N, every other term afterwards for c sub n falls in between a sub n and b sub n for that value of n. If that occurs for every n greater than this capital N, then c of n is squeezed in between this a sub n for eternity after this point n. If it's squeezed in between there, its limit must be the same as those two, because those two share the same limit. So we're finding a point where our third sequence is contained within the other two sequences, and if that continues on for eternity, then we can conclude that the limit is equal. It might take a moment to wrap your head around it, and it's kind of confusing at first, but I assure you it's super powerful and it's actually really cool. And let's take a look at an example that uses the squeeze theorem. So we have this sequence, a sub n equals -1 to the n times 1 over n factorial. We want to show that it converges and find its limit. So if we were to just do this traditionally, and we take the limit as n approaches infinity of -1 to the n times 1 over n factorial, then we would say that this is equal to the limit as n approaches infinity of -1 to the n times the limit as n approaches infinity of 1 over n factorial. The first term is actually not that easy to calculate, but the second one we can say goes to 0. The first one we run into that issue of like, oh, it oscillates between -1 and 1, so that's not great. So we may need another way to approach this. So what we'll do is we'll take advantage of the fact that -1 to the n oscillates between -1 and 1. And we'll consider just any arbitrary value of n. We don't know if it's odd or even, because that would give insight into what -1 to the n computes to. But what we can say is just for any random arbitrary value of n, we know that a sub n will fall in between 1 times 1 over n factorial, or -1 times 1 over n factorial. Right, we're just handling that first term there, that either it's -1 or 1, but regardless, a sub n will fall somewhere in between there, because in this case, it will either equal this, or it will equal this. But since we don't know what it is, since we don't know the value of n, we'll throw in these inequalities here. So let me get rid of the 1 and the -1 and just add a sign to here. Okay. So now if we replace a sub n with the actual formula, what we're claiming is -1 over n factorial is less than or equal to negative 1 to the n over n factorial, less than or equal to 1 over n factorial. And it's kind of an absurd thing to claim. Like, yeah, it might be kind of obvious, but it's sort of thinking of like, why do I have to claim this? Like, why would I even say this in the first place? And the answer for that is to use the squeeze theorem. Because we know computing the limit of this is kind of hard, but now we know for all values of n, this term, which is a sub n, falls in between these two values. So in fact, let's give new names to these sequences. Let's let a sub n be equal to negative 1 over n factorial. Let's let b sub n equal 1 over n factorial. And let's let c sub n equal negative 1 to the n over n factorial. What we're going to try to do now is use the squeeze theorem. From before, we said if this inequality holds, c is in between a and b for all n greater than n, which is what we have here, this holds true for all n, then if these two limits equate to the same value, we can conclude that the limit of our third sequence equals L. So let's hope that those limits do equate to the same value, and if they do, then we're good. If not, then no good. So let's consider the limit of the left-hand side, which would be equal to the limit as n approaches infinity of negative 1 over n factorial. Well, that's just equal to negative 1 times the limit as n approaches infinity of 1 over n factorial, which we said was equal to 0, so negative 1 times 0 equals 0. Cool. Now let's compute the limit of the right-hand side. So this is the limit as n approaches infinity of 1 over n factorial. That's just going to be equal to 0. So this limit goes to 0. This one goes to 0. This red one in the middle, we said it's in between those two other sequences for the duration of time as for all values of n. So as n approaches infinity, this must also go to 0, so the sequence converges to 0 by the squeeze theorem. So that is one really cool application of the squeeze theorem, and we can see that it helps us out a lot because we didn't have to handle that nasty limit to start with. Let's do one more example. So first, we want to find a sequence whose first 5 terms are those terms, and then determine the value of a sub 6, and determine whether the sequence converges or diverges. So we need to construct a formula for a sub n. So we see that it's a fraction, and we see that it's going from negative to positive to negative to positive to negative. So we can handle the sign first, we can handle the numerator, and we can handle the denominator, and then compose them all together. So let's do the sign of it first. So a sub 1 is negative, a sub 3 is negative, a sub 5 is negative. So whenever our n value is an odd number, we need a negative in front of it. So we can do that by saying that it'll be negative 1 to the n times something. Right? And now when n is even, we have a positive 1, which is good. So now we'll want to have a fraction, because all of the terms are fractions. Let's look at the denominator. 1, 2, 6, 24, 120. So it might not immediately jump out to you what the common pattern is, but let's see. Going from 1 to 2, we can think of adding 1 or multiplying by 2. 2 to 6, maybe we're multiplying by 3 or adding 4. 6 to 24, we're adding 18, which seems to start getting weird because the next one will be adding 96. But if we go on this pattern of multiplying, 6 to 24 multiplying by 4, 24 to 120 multiplying by 5, we should start to notice that the denominator is actually n factorial. Pretty cool. The numerator might be a little bit more tricky. 2, 8, 26, 80, etc. How are we going to do that? This is where we sometimes have to be a little bit creative. We can notice that 2 is pretty close to 3, 8 is pretty close to 9, 26 is pretty close to 27, 80 is pretty close to 81, 243. These are the powers of 3. They're just one less. So we can rewrite the numerator as 3 to the n minus 1, and that's going to be our sequence. So that means a sub 6 will be equal to negative 1 to the 6th times 3 to the 6th minus 1 over 6 factorial. You can compute this out. Should be 728 over 720, which is equal to 91 over 90. Now we have to see if the sequence converges. So we'll take the limit as n approaches infinity of negative 1 times 3 to the n minus 1 all over n factorial. So we've dealt with this negative 1 to the n in the past, where the sign changes and sometimes it converges, sometimes it diverges. When would it converge? Well, if the sign changes, that's fine, as long as we're approaching some smaller and smaller value. So if we scroll back to our picture of the squeeze theorem here, look at c sub n. The terms are going negative to positive, but they're slowly approaching the 0, so it is possible to converge. We just need the absolute value of the terms to approach, in that case, 0. So let's take a look at 3 to the n minus 1 over n factorial. Let's just take a look at this limit, and we can say that if this limit approaches 0, then our original limit will also approach 0. For really large values of n, this minus 1 in the top doesn't really do anything, so we're just left with 3 to the n over n factorial. And if you plug in infinity, you'll get infinity over infinity, L'Hopital it out, and that would be all good and dandy. However, there's a nicer way to look at it. Start thinking of values of n and start to compare the two values. So like, when we consider n equals 7, we have 3 to the 7 over 7 factorial, which is equal to 729 times 3, which is 2187 over 5040. And for the next value of n, it would be 3 to the 8 over 8 factorial. But we can rewrite this as 3 to the 7th times 3 over 7 factorial times 8. So actually what we're doing is we're multiplying the previous term by 3/8. And if we go to the 9th value, which is 3 to the 9 over 9 factorial, we'll be multiplying the previous term by 3/9. So we're progressively multiplying by these fractions, which means we're making the number smaller and smaller. So as n gets larger and larger, we kept on multiplying by these fractions, which makes the number smaller and smaller. So indeed, the limit will approach 0. So this will converge to 0. So, I apologize for my explanation of that being quite verbose and not really mathematical, but this is a really helpful skill to have, where you can just qualitatively go through a limit and explain to yourself why it must converge. So that's exactly what we did here. So there you go, that's your introduction to sequences. Hope you enjoyed it. Next time we'll look at series, and then we'll keep on going and learn a lot more. As always, take care.